Welcome to this lesson on heat economics. We will look into the economic assessment of heat sources and storage systems. My name is Alexandros Danielidis. The aim of this lesson is to outline the importance of techno-economic assessment for heat systems. After completing this video, you will be able to describe the different steps required for techno-economic assessment, or TEA, distinguish the different purposes that TEA can serve, and explain the relevance of TEA in decision-making. In previous sessions, you have learned about different heat sources, heat storage technologies, and heat supply systems. You have discussed the relevant physics and processes of heat sources and storage, and the dynamics of heating systems and heating demand. When designing a heating system to cater to heat demand at any scale, the economic performance of the system also needs to be considered. This is the point where the techno-economic assessments comes to the fore. Let's look at an example of how techno-economic assessment can be used to indicate increasing feasibility of a geothermal system. The starting point is the theoretical capacity. This indicates the amount of heat that is present in the subsurface in the fluid rock system. The theoretical potential outlines the amount of heat that can be converted from the theoretical capacity based on the expected conversion efficiency. The technical potential is the amount of theoretical potential that is recoverable based on current technology, considering a recovery factor. And lastly, the techno-economic potential is the part of the technical potential that is commercially viable within a range of economic conditions. The economic aspects to consider related to capital expenditures, such as equipment or construction works, operational expenditures like maintenance, labor costs, and production costs for operating the facility. Abandonment costs related to decommissioning and safely stopping operations can also be relevant. Depending on the process, fuel costs could be incurred as well. Lastly, revenues are generated by selling the produced heat. Several economic indices are used for this assessment. Here we will focus on the net present value and the levelized cost of energy. The net present value is the sum of the net cash flows, revenues minus expenses, considering the time value of money. The latter is computed based on the discount rate that is applied for each time period considered. The levelized cost of energy is the net present cost of energy over a certain production lifetime. It is computed as the fraction between the sum of discounted costs over the sum of discounted energy production. The levelized cost of energy refers to energy and is the more general term, while the levelized cost of heat refers specifically to heat. The index gives us a meaningful value of per unit of energy and is often used to compare different technical choices or different ways to produce energy. Let's look at an example of techno-economic assessment using a simplified process model of a geothermal doublet. The process model describes the physics during geothermal production. These include the production well, the production pump, the heat exchanger, the injection pump, and the injection well. The capital costs here include the drilling the wells, buying the pumps and replacing them if they fail, and also purchasing the heat exchanger. The operation costs include maintenance and running the pumps. Abandonment costs are also considered for safely decommissioning. Lastly, revenues are generated from selling the heat. We consider 30 years for the project lifetime and an annual discount rate of 10%. Using a heat price of €40 per megawatt hour, we are generating a net present value of €8.5 million. The levelized cost of heat in this case is €29 per megawatt hour. The break-even point is around 7.5 years. To investigate the sensitivity of the economic output, we consider changing the discount rate to 15%. This results in a decrease of the net present value to €2.7 million. The break-even point is now about 12 years. Notice that the levelized cost of heat is also higher and amounts to €35 per megawatt hour. Back to our initial example, let's see now the relationship between the net present value and the levelized cost of heat. Setting the heat price to be equal to the levelized cost of heat results in a net NPV of 0. A different way to look at this is that for a heat price above the levelized cost of heat, a positive NPV will be generated. The levelized cost of heat is a powerful index when comparing different options. In this example from the International Energy Agency, you can see the resulting levelized cost of heat for different types of heat pumps compared to gas for heating and compared to gas and air conditioning for heating and cooling. Notice how, depending on the country, different options are more cost effective. Gas heating is cheaper than heat pumps in the UK, but more expensive in Korea. Additionally, the levelized cost of heat can be used to compare different technologies. In this plot, you can observe the order of magnitude decrease for solar PVs and a significant improvement of onshore wind farms to produce electricity. Geothermal sources have been stable over time, but remember that they can also provide baseload energy 24 hours per day compared to intermittent sources such as solar and wind. Summarizing our lesson, we have discussed how techno-economic assessment includes multiple aspects such as process models and economic parameters like the discount rate. The end result is the combined analysis of energy and monetary value or cost. This type of assessment can serve different purposes such as options within an individual project, a comparison between energy sources or energy systems as a whole. It is therefore important for decision making and system design. Thank you for your attention.